Hello students, can you hear me?
Yes, sir.
Yes,
Thank you for the confirmation. Let me start today's class. Can you see the presentation?
Yes, sir.
yes,
Yeah, I think you all know me. I am Venkat Subbareddy, a research scholar at the University of Hyderabad. So I am here to solve some problems from assignment 3. This assignment is not actually this year's assignment, previous year's assignment, but solutions for these problems may help you to solve this year current year problems. So let me solve some of those. So here is the first problem. Which one of the following maps is not an isomorphism? So I think you all know when a linear transformation is called an isomorphism. So let me write it. The first problem, we call a linear transformation T from a vector space V to W is an isomorphism if and only if T is both 1 to 1 and on to. In the given question, it is asking which one is not a linear transformation. So we will check one by one option. So here the first option is T from R cube to R cube. Given that T of x comma y comma z equal to some matrix times x y z. So to check it is a linear to check it is one isomorphism or not, it is enough to check it is 1 to 1 and onto. In fact, we don't need to check the onto because here the given domain and codomain both are R cube. That means the dimensions of each vector space is same. So it is just enough to check whether the linear transformation is 1 1 or not. From that we can say we have one theorem, that rank nullity theorem. From that we can say rank of T plus nullity equal to dimension of. From this we can say if it is 1 1, then we can say onto, because the dimensions of domain and codomain are equal, we can say that. So we will just check 1 1. So the first option is T from R cube to R cube given by T of x comma y comma z equal to the matrix 0 1 1 minus 1 0 minus 1 1 1 3. After the class I am going to share this PDF file with you, so there you can check the options. I'm writing the options directly, so you don't need to worry. So the corresponding matrix of this linear transformation is nothing but A equal to the given matrix 0 1 1 minus 1 0 minus 1 1 1 3, is the corresponding matrix to the linear transformation. So to check it is 1 1 and R2, it is enough to check the determinant of this matrix, because whenever its inverse is not 0, then we can say the matrix is inversible, and hence it is 1 1 and onto. So we will just check whether mod A is 0 or not. From this we can say the linear transformation is 1 1 or not. So I think you all know how to calculate the determinant of matrix A. Determinant of A is nothing but, here the first element is 0, so we don't need to calculate for this, and the second element is 1, so minus 1 times the determinant of this matrix, 0 minus 1 1 3 plus 1 time
In the question, it is -3.
minus 3. Yes, thank you. So this is nothing but 0 plus 1, so this is minus 1 plus this is minus 1 again, so this is minus 2, which is not equal to 0. So the matrix A is invertible. That implies the linear transformation corresponding to the matrix A is from R cube to R cube is 1 1, hence it is onto also. So the first option is not correct option, because it is asking which one is not an isomorphism. So let's check the second option. Second option is T from M2 cross 2 comma to P3, where P3 is nothing but the vector space of all polynomials of degree at most 3. So the linear transformation is nothing but T of A B C D is equal to B times B plus D minus B times X plus CX square plus 2A plus C times X cube. So it is in to check whether this linear transformation is 1 1. It is enough to check T is kernel T is singleton set 0 or not. This is because if you check here the dimension of the domain here M2 cross 2, the dimension of this M2 cross 2 is nothing but 4, and similarly the dimension of P3 is also 4. So whenever dimension of domain and codomain are same, we have T is 1 1 if and only if kernel T is equal to 0. So it is enough to check for this linear transformation kernel T is singleton set 0 or not. So we are going to check that. From that we can say the linear transformation is isomorphism or not. So let's take one element in kernel T and we will prove that element is 0. Let the matrix A B C D belongs to kernel T, kernel T, that implies T of this matrix is 0. By the given linear transformation, we have the value of this is nothing but P plus D minus B times X plus CX square plus 2A plus C into X cube. This is equal to 0. If we compare the coefficients of constant, compare the coefficient constant and the coefficients of x square x cube, we get all the constant terms are zeros. That means b equal to 0, d minus b equal to 0. From this we can say d equal to 0, c equal to 0, 2a plus c equal to 0. From this we can say a equal to 0. That means the matrix is nothing but the 0 matrix only. That is a b c d equal to 0 matrix. So it is proved that kernel T is nothing but singleton set 0. So T is 1 to 1. Here now we'll check the third option. Third option is T from P3 to P2. The space of all polynomials of degree at most 3 to space of all polynomials degree at most 2. Sorry, in the domain degree should be at most 3. So the linear transformation is nothing but the derivative. That is T from P3 to P2 given by T of P of x, where P of x is a polynomial of degree at most 3 is P dash of x. So if you can see here for the vector spaces P3 and P2, for this P3 the dimension is 4, but here the dimension of codomain, that is dimension of P2 is 3. So from this we can say dimensions of the both domain and codomain are not equal. I am saying this because whenever T is 1 1, we need not to say T is onto here because the dimensions are differ. So we need to check both 1 1 and onto here. But firstly we will check 1 1. That means similar to the option B. We will check that kernel T equal to singleton set 0 or not. Here we have to check both 1 1 and onto because the dimensions are differ. So let's take a polynomial p of x in kernel T. That implies T of p of x is 0. That implies p dash of x equal to 0. Here we are taking p of x is in P3. That means p of x, let me write here. So p of x is a polynomial of degree at most 3. Let me write it as a plus bx plus cx square plus dx cube. So from this you can say p dash of x equal to 0 implies the derivative is nothing but p plus 2cx plus 3d x cube, that equal to 0. So by comparing the coefficient constant term and the coefficients of x square, this is x square. So we get b equal to 0, c equal to 0 and d equal to 0, but we don't get anything about a. So we can take a equal to any constant term k, any constant k, where k is a scalar. So for any scalar a equal to k, the derivative of p dash of x equal to 0. That means we have p of x belongs to kernel T if and only if p of x equal to constant term k. That implies this constant need not be 0 always. So it can be some other scalar. So we cannot say kernel T is not we cannot say kernel T is singleton set 0. So that implies T is not 1 1. To check T is isomorphism, we have to check both T is not 1 1 here. So to check isomorphism, we have to check T is both 1 1 or not. But first of all, it is not 1 1. So whether it is onto or not, we don't matter. T is not 1 1. So we can say T is not isomorphism. This is what they are asking in the question. Which one is not an isomorphism? So option 3 is the correct option. For the option 4, we can directly check that by taking kernel T equal to 0. For this kernel T equal to, we have to check that kernel T equal to 0. That implies, let's take some element A in kernel T. That implies T of A equal to 0. That implies we have that A transpose equal to 0. So from this we can say A equal to 0. So kernel T is nothing but singleton set 0. So we can directly say T is 1 1 here for the fourth option. So the only option correct is option C. Do you have any doubt in this question?
சார்
Yes.
ஃப்ரெண்ட்ஸ் எல்லாம் ஜாயின் ஆக மாட்டேங்குன்னு சொல்றாங்க சார்.
Sorry ma, I don't know Tamil. Hello.
சார்
Yeah. Can you ask me in English?
Sir, our friends are willing to join, sir. Please allow them, sir.
Okay. Okay. Sorry, I did not see. So the second problem. Okay. Do you still have any doubt here? Otherwise, I will proceed with the second problem. Okay. I hope nobody have any doubt.
Sir,
So, yes.
sir, in this question I don't have any doubt, but in our assignment the same question is there. Not same question, similar question is there.
Okay.
Which one has a mapped isomorphism?
Okay.
All the four options are satisfying the question.
Is it?
Yes, sir.
Okay. You write that in that discussion forum. I'll solve there. I'll explain you there.
Okay.
Actually, I have not
Okay,
seen
sir.
that assignment.
Okay, sir.
So the second problem here is, it is given a linear transformation from P2 to P3 as T of P of x equal to this x square P double dash x minus P dash of x plus 2x Px. So it is given that A is the matrix representation of T with respect to the standard basis. We have the standard basis for P2 as 1x and x square, and for P3 1x x square and x cube. So the question is, then the sum of the elements in the third row of A. It is the question. For that, firstly let me write the matrix A here corresponding to this linear transformation. So given linear transformation is T is from P2 to P3 by T of P of x as x square times P double dash x minus P dash of x plus 2x P of x. So let me write the standard basis for P2 and P3. We have the standard basis for P2 as 1x and x square. Similarly for P3, 1x, x square and x cube. If we change the corresponding bases, actually we have infinite number of bases for p2 and p3 respectively. So if by changing the bases, we will get different kind of matrices. So it is given, but here it is given that we have to calculate the matrix A corresponding to the standard ordered basis for p2 and p3. So we are considering these two ordered bases and we are calculating the matrix A. So we'll see what the matrix A is. So firstly, let me calculate the images of elements in image. Let me consider the images of this element, the basis for the domain. That means t of x, t of 1 is nothing but x square times p double s. P double s is nothing but 0 minus p dash is also 0 plus 2x. P of x is 1. That means it is nothing but 2x. So let me write this as linear combination with the basis of p3, because t of 1 is contained in p3 because it is a image. So I have to write the element 2x as linear combination with the elements of basis p3 with this basis. So how to write? 1 times 0 plus 2 times x plus 0 times x square plus 0 times x cube. Similarly, let me calculate the images of x and x square under this linear transformation. Then we can write the matrix corresponding to this linear transformation. So t of x with the given linear transformation is nothing but x square times 0 minus p dash is 1 plus 2x into x. This is nothing but minus 1 plus 2x square. So again write it with the linear combination of the elements corresponding to the basis p3. So we'll write minus 1 times 1 plus 0 times x plus 2 times x square plus 0 times x cube. Similarly, for the element x square, we have t of x square equal to x square times p double s is nothing but 2 minus p dash is 2x plus 2x times p of x is x square. So this is nothing but minus 2x plus 4x square. Sorry, plus this is 2x minus 2x plus 2x square plus 2x cube. So writing it with the linear combination, we have 1 times 0, 0 times 1, we can write anyway. So minus 2 times x plus 2 times x square plus 2 times x cube. So now writing the matrix corresponding to this linear transformation, we have that A is equal to, now write the coefficients of, where is the answer? So now we have the coefficients for this image of t of 1 as 1, here 2, 0 and here 0. So we have to write these coefficients in column form. That means 1, 2, 0 and 0. Similarly, for the next element t of x, we have minus 1, 0, 2 and 0. Similarly, for the third element, we have minus 2, 2, sorry, first is 0. This is 0, minus 2, 2, 2. So this is the matrix corresponding to linear transformation T with respect to the standard ordered basis. So the question it is asked here is the sum of the elements in the third row of A. So and then the sum of the
Excuse
element.
me, sir.
Yes.
If you don't mind, allow our friends to join, sir.
Okay.
Thank you, sir.
So from this you can say, so sum of elements in the third row is equal to 4. That is the correct option. Let me see in which option it is. So this is the correct option. Do you still have any doubt? This is how to write a linear transformation into matrix form. Anybody have any doubt?
No, sir.
Thank you. So third problem is, which of the following matrix is diagonalizable? So given 4 options, we'll check which one is the diagonalizable. I think you all know when a matrix is called diagonalizable. So we call a square matrix A of order some n cross n is diagonalizable if AM is nothing but algebraic multiplicity if AM of each eigenvalue equal to GM. GM is geometric multiplicity of corresponding eigenvalue. So for each option we will check which one is diagonalizable or not. So the given matrix is 1 1 minus 1 minus 1. So firstly we will calculate the eigenvalues. This problem is a little lengthy. Anyway, we will see. So firstly we will see what are the eigenvalues. For the to calculate the eigenvalues we have to see characteristic polynomial, that is nothing but characteristic polynomial of is modulus of determinant of x minus xi minus a, that is nothing but determinant of x minus 1 1 minus 1 x plus 1. So the determinant of this matrix is nothing but x square minus 1 plus 1. So characteristic polynomial is nothing but x square. So from this you can say that eigenvalues of this matrix are zeros only. Eigenvalues are 0, 0. But algebraic multiplicity of eigenvalue 0 is nothing but is 2, that you can see because it is repeating twice. Am of 0 is equal to 2. But you have to see, you have to check the geometric multiplicity of this corresponding eigenvalue also. Whenever if the geometric multiplicity is also equal to 2, then we can see this matrix is diagonalizable. So to check, now we will check GM of the eigenvalue 0. So for this we have a formula that geometric multiplicity is nothing but the order of the matrix 2. Sorry, let me write the formula first. Order of the matrix minus rank of A minus the corresponding eigenvalue. I am denoting it with lambda I. So here we can see that, so for the given corresponding eigenvalue 0 we have that rank of, so firstly let me write the matrix what is A minus lambda I. we have a minus lambda I is nothing but a minus, here lambda is 0, so 0 times I, this is nothing but a. So rank of a minus lambda I is nothing but rank of a, that is equal to 1, that you can see from the matrix. Because determinant is 0, rank is 1. I don't mean whenever determinant is 0, rank is 1. For this corresponding matrix 1 1 minus 1 minus 1, we have the rank is 1, that you can calculate. So from this we can say geometric multiplicity of 0 is nothing but 2 minus 1, that is equal to 1, which is not equal to algebraic multiplicity. So therefore A is not diagonalizable. In the similar way, we will check for the remaining matrices also. The second option is 0 minus 1 0 0. Can you say what are the eigenvalues for this matrix by just simply looking at this matrix? Does anybody know how to check? Or can you say the eigenvalues for upper or lower triangular matrix?
Diagonal elements.
Yes, upper triangular matrix. So whenever we have a upper or lower triangular matrix, let me write for one matrix. We have an upper triangular matrix, that means these diagonal elements are non-zero. Non-zero means these can be any scalars, but the elements below the diagonal matrices diagonal is zeros, and this above the diagonal elements are non, can be anything. Just we have that the elements below the diagonal are zeros, then we have the eigenvalues for this matrix are this, whatever the elements in the diagonals. Similarly for upper triangular and lower triangular also. So by this we can see eigenvalues are zeros, and algebraic multiplicity of 0 is nothing but 2. So now we will check the geometric multiplicity. Geometric multiplicity is nothing but the order of the matrix, that is nothing but 2 minus rank of a minus 0 times I. This is nothing but 2 minus rank of a, that is equal to 2 minus 1. Here we can see the rank of the matrix A is 1. So this is equal to 1, which is not equal to the algebraic multiplicity. So this matrix is also not diagonalizable. Similarly, for the third option, we have the given matrix is 2 0 1 2. So by the same, we can say the eigenvalues are 2 comma 2, and algebraic multiplicity of eigenvalue 2 is equal to 2. Now we will check the geometric multiplicity. So geometric multiplicity of 2 is nothing but order minus rank of a minus 2I, that equal to 2 minus rank of the matrix 0 0 1 0. So this you can say what is the rank of this matrix, that is nothing but 1. So this is equal to 1, which is not equal to the algebraic multiplicity. So we can say this matrix is also not diagonalizable. So for the fourth option, we have the given matrix is 1 1 0 minus 1. So here we have the eigenvalues are 1 comma minus 1, and the algebraic multiplicity corresponding to each eigenvalues is 1 1. Algebraic multiplicity of 1 is equal to 1. Algebraic multiplicity of minus 1 is also 1. For geometric multiplicity, we can check this in two ways. Firstly, let me calculate in the similar way how we did for the remaining options. Then I will explain the another way also. So geometric multiplicity of 1 is nothing but the order of the matrix is nothing but 2 minus rank of A minus I. This is equal to 2 minus rank of the matrix A minus I is nothing but, for the given matrix, so by subtracting with I we get 0 1 0. This is minus 2, I suppose. Is it correct? 1 1 0 minus 1. But we are getting 2 minus 2, that is equal to 0.
Rank is 1.
Yes, right.
Yes, sir.
Yes,
Hello.
Rank of the matrix is 1.
yes. Thank you. Somebody speaking? Yes, any doubt? Here the rank is 1 because determinant is 0, so we have one non-zero submatrix. So this is equal to the algebraic multiplicity of 1. We have to check for the other eigenvalue also. Let me calculate that. Geometric multiplicity of minus 1 is nothing but 2 minus rank of A minus A plus I. So for this matrix we get 2 minus rank of A plus I is 2 1 0 0. For the given matrix 1 1 0 and minus 1. So rank of this matrix is nothing but 1. So we'll get 1. This is equal to algebraic multiplicity. So for each corresponding eigenvalues we have algebraic multiplicity equal to geometric multiplicity for each eigenvalue. So A is diagnosable. So here is the another method how to check the geometric multiplicity for each eigenvalue. We have a inequality that geometric multiplicity is always less than or equal to algebraic multiplicity, and it is always greater than or equal to always greater than 0. So from this we can say 0 is less than geometric multiplicity is less than or equal to 1. So there exists no integer in between 0 and 1 except 1. By this inequality we have 0 is less than geometric multiplicity is less than 1. So geometric multiplicity has to be equal to 1. In a similar way for the remaining eigenvalue also, for the eigenvalue minus 1 also we have 0 is less than geometric multiplicity less than or equal to am. Here geometric multiplicity is 1, so we get 0 is less than geometric multiplicity is less than or equal to 1. So geometric multiplicity equal to 1. So from this method also we can say this matrix is diagonalizable. So let me solve the fourth problem.
Sir, I'll ask you one bit. I'll share my screen and I'll I'll ask you one doubt, sir.
Yes, please. Wait, I'll stop sharing.
Yes, sir. I'm asking about this question, sir. Yes, sir. I'm asking about that question, sir.
Yeah, okay. Can you show it again? Yeah. A be a square matrix of order 3 cross 3 with eigenvalues 1, 1 and 4 and rank of A minus I equal to 2, then the matrix A is diagonalizable but not invertible, invertible but not diagonalizable, both diagonalizable and invertible, neither diagonalizable and invertible. Here you can check the invertibility because determinant is nothing but the product of the eigenvalues, so we can say determinant is 4 here. So from that we can say it is invertible, but we have to check the diagonalizability. For the diagonalizability, in the similar way which I told you the second method. So for the geometric multiplicity of 4, we can say it is 1. So for the eigenvalue 4, geometric multiplicity is equal to arithmetic. So okay, wait, let me write. Can you stop sharing? I'll explain that.
Yes, sir. Yes, sir.
So it is given that A has eigenvalues 1 comma 1 comma 4 and rank of A minus I is equal to 2. So from this we can see determinant of A is 4. So it is invertible. So for the diagonalizability, we have to check the algebraic multiplicity of each eigenvalue. We have algebraic multiplicity of 1 is equal to 2. So for geometric multiplicity, we have order of the matrix 3 minus the rank of the matrix A minus I. This is equal to 3 minus 2, that is equal to 1, which is not equal to the algebraic multiplicity. So AM is not equal to GM. A is not diagonalizable.
Thank you, sir.
Yes. Is it clear now? Of course, for the remaining eigenvalue 4, we have both are equal.
Yes, sir. Thank you, sir.
But for the eigenvalue 1, it is not equal. So we can say A is not diagnosable. So which problem? Fourth problem. So the minimal polynomial of this matrix is, I think you all know how to calculate the characteristic polynomial. From that only we will calculate the minimal polynomial also. For the problem is the given matrix 4 0 minus 3 4 minus 2 minus 2 4 0 minus 4. So let me call it as A. So characteristic polynomial of A is nothing but determinant of A minus xi. That is nothing but the determinant of 4 minus x, 0 minus 3, 4 minus 2 minus x, minus 2, 4, 0 minus 4 minus x. You all know how to calculate the determinant of this matrix. This is nothing but 4 minus x times minus 2 minus 6 into minus 4 minus x minus 3 times minus 8 minus x. Sorry, this is plus, right? I think so. So from this we can see this is, let me write it directly because we are running out of time. From this we get lambda plus, sorry, x plus 2 into x square minus 4. I think so. Maybe it may be differ by a sign also, or x plus 2 times x square minus 4. You do the calculations here. You will get one of these two. So from this characteristic polynomial we have that x plus 2 times x plus 2 whole square into x minus 2. We have a condition that, so we have that all the roots of minimal polynomial are also roots of characteristic polynomial. So from this we can see the minimal polynomial of A can be one of these two. That means x minus 2 into x plus 2 or x plus 2 whole square into x minus 2, because we have only two possibilities. That here we have that the characteristic polynomial is x plus 2 whole square into x minus 2. That means the roots of this characteristic polynomial are 2 and minus 2. That is eigenvalues are 2 comma minus 2 comma minus 2. So these are the only roots of minimal polynomial also. But minimal polynomial can be, in minimal polynomial the roots can be repeated or non-repeated, but at least each root should appear at least once. So by that property we can say the minimal polynomial of x can be any one of these two. Now we have to check which one is the minimal polynomial among these two. So for the minimal, let me write how to say. So corresponding to this first polynomial, we will check what is the value of this matrix. So we will check what is the matrix a minus 2i into a plus 2i. If we get this equal to 0, we can say this is the minimal polynomial. Otherwise the second one is the minimal polynomial. So for the given matrix we have that this is nothing but a minus 2i, that is 2 0 minus 3 4 minus 4 minus 2 4 0 minus 4 minus 2, this is minus 6 into a plus 2i, this is 6 0 minus 3 4 0 minus 2 4 0 minus 2. Do the product, we get that this is 0. You can see that all becomes 0. I'm just writing, let me write the values also, then we can observe 12 minus 12, here it is 0. So minus 6 plus 6. Here 24 minus 16 minus 8, 0. 12 plus 8 plus 4. Sorry, this is minus 12 plus 4. Third row will become 24 minus 24, 0, minus 12 plus 12. So you can see this is equal to 0. That means minimal polynomial of A is nothing but x minus 2 times x plus 2. Of course, if we apply the, of course, for the second polynomial, this for this polynomial also we will get a plus 2i whole square into a minus 2i also equal to 0, because this is nothing but we will get a plus 2i into a minus 2i into a, here we can write a plus 2i, this is, we will get this as a plus 2i times 0. This is nothing but 0. Of course we will get the we will get this equation also equal to 0, but we have that minimal polynomial is nothing but the least degree polynomial. Among these two we have that the first polynomial is the least degree, so we say the first polynomial is the minimal polynomial. So among the options, so we get that the minimal polynomial is x minus 2 into x plus 2. This is nothing but x square minus 4. So option C is the correct. We have 10 more minutes. Let me solve the fifth problem. So given a linear transformation t from r square to r square with t of 1 comma 0 equal to 1 to t of 1 comma 1 equal to 0 comma 2, then it is asking the value of t inverse of 2 comma 3. So we will see how it is. We have that whenever t is a linear transformation and t is invertible, we have that t inverse is also a linear transformation. So we will use that property here. Fifth problem, t is from r square to r square given by t of 1 comma 0 equal to 1 comma 2, t of 1 comma 1 equal to 0 comma 2. So from this we can say the linear transformation is invertible. By just doing the by writing the linear transformation into matrix form and doing the determinant, we can check that t is invertible. So we can say t inverse is also a linear transformation. It is asked to calculate the t inverse of 2 comma 3. So from the given conditions we can say that we have to calculate this value. From the given conditions we can say that t inverse of 1 comma 2 equal to 1 comma 0 and t inverse of 0 comma 2 equal to 1 comma 1. This is nothing but I am just applying the t inverse on both sides of these two equations. So now I think you know how to calculate by just writing 2 comma 3 into linear combination of 1 2 and 0 2. So firstly let me write 2 comma 3 as a linear combination of 1 comma 2 and 0 comma 2. From this we will calculate the values of a and b. So for this we have a equal to 2, 2a plus 2b equal to 3. That implies b equal to 3 minus 6 to be equal to this. This is minus 3. So b equal to minus 3 by 2. So let's substitute this. We'll get that 2 comma 3 is a linear combination as 2 times 1 comma 2 minus 3 by 2 times 0 comma 2. Now apply the linear transformation t inverse to this equation. we get T inverse of 2 comma 3 equal to T inverse of 2 times 1 comma 2 minus 3 by 2 times 0 comma 2. Because T inverse is linear transformation again, so we can write this as 2 times T inverse of 1 comma 2 minus 3 by 2 times T inverse of 0 comma 2. We already have the values for T inverse of 1 comma 2, that is T inverse of 1 comma 2 is 1 0. This is 1 comma 0 minus 3 by 2 times 1 comma 1. So by just doing addition we get 2 minus 3 by 2 comma, this is minus 3 by 2. This is nothing but 1 by 2 comma minus 3 by 2. Is it correct?
Sir,
Yes.
sir, we have few doubts from week 3 assignment, sir. Can you explain now, sir?
From current week?
Week 3, sir.
Okay.
We will
Hello,
share,
sir.
sir.
Wait 1 minute. There is a mistake I think in this calculations.
Hello, sir. In this
Yes.
equation, 2a
Here.
plus 2b equal
Yes.
to
Yes. Yes.
3.
Yes.
If
Here we
a
have a
is
mistake.
2,
Yes. Here we have 3 minus 4 equal to minus 1.
right.
1 by 2. By the calculations we have 2 minus half, and this is minus half. This is equal to 3 by 2 comma minus half. So from this we have I think the option B is correct. Yes. Yes. In a similar manner you can solve the other problems also. These are nothing but just calculating the eigenvalues and characteristic polynomials. From those we can check the options.